Good morning. First of all, I would like to thank Dr. Keith Kendrick, who did all the work in organizing this. So I'll be briefly talking about comparison between task and rest. So with fMRI, mostly with task, the idea is you present different kinds of stimulus, and then using subtractive logic, you can then find very specific changes pertaining to different tasks. And since as a graduate student, I didn't know any better, so I decided to do resting state. And so again, so this is task, and with resting state, the idea is very similar, excepting you don't have to do anything, just scan a subject while at rest, then look at the frequency spectrum, and then analyze the data in identical fashion. And then with sensory motor tasks that we did, what we found out was it was very similar to the task finger tapping response. And because Carl Friston had defined functional connectivity as temporal correlation between a task-related neurophysiological signal, and we were observing this during rest, therefore we defined this as resting state functional connectivity. And again, the point is not to criticize task or something, but it's so easy to think of many cases where you cannot simply do task, like in infants and clinical population, and in many other cases, also with task activation, typically you could only do one task at a time. And so, although most of my papers got rejected, but still, I think they still get rejected. But that's why it was very easy to just collect a bunch of data, scan them, and then do different kinds of analysis, and then you could find different activation pattern. So for today, we are going to, or at least I'm trying to address from a couple of different perspectives. But the first thing we should understand is the fMRI signal that we measure is a convolution of neuronal activity with hemodynamic. And so by changing one or the other, we get a difference in fMRI signal. And so this is like a hypercapnic stimulus that we did many years ago. And this was to show how with task activation, you could, like in the top left, task activation, you could find the sensory motor cortex. And then with resting state, you could identify the sensory motor cortex. But when you gave subject to breathe CO2 for several minutes, these fluctuations was diminished, and that the resting state functional connectivity was severely diminished also. After the subject breathed room air, and when we collected resting state, then we could again recover these fluctuations, again suggesting that the signal that we see during rest has some biophysical meaning. Dr. Mehta will be talking in more detail about some of the pharmacokinetic study, but this is another example, study done by Vesa Kivanimi, where he gave subjects thiopental, and in this case, one saw increased in fluctuations in the visual cortex. Similarly, Scott Pelt here scanned subjects during servoflurane, and during light anesthesia, what he observed was there was connectivity within the left hemisphere, connectivity within the right hemisphere, but no connectivity between left and right. And with deep anesthesia, these both interhemispheric as well as within hemisphere connectivity was significantly reduced. Again, suggesting that for different kinds of studies like anesthesia and so on, this could also be used as a way to better understand. So between task and rest, I'll try to cover these three. The first is that the task response, is it dependent on the resting state fluctuation and vice versa? The simple reason being they share the same neurovascular model, right? The second is the spatial organization of task and rest. So while, we and others have shown that for finger tapping, you have sensory motor cortex, and then the resting state network overlaps, can it be generalized to other tasks? And third is to look at some dynamic interaction between multiple regions. So this is like trying to say that, with task, is the regions that is typically shown, is that the only region that changes? So for the first one, how do the amplitude of the resting state fluctuation relate to task activation? So this is a very well-known phenomena because the fMRI signal is, again, as I mentioned, is a convolution of neural function, neural activity, and hemodynamic function. What researchers have done is use a hypercapnic stimulation like breath hold and look at the changes during breath hold, because with breath hold you simply get a response which is due to pure hemodynamics. There is no neuronal component. So by dividing with the change during task, then what we are doing is we are calibrating based on we're calibrating the vascular effect. This is showing, I don't know which one the point. So on the left left top is finger tapping. Left bottom right is breath holding. Top right is breath holding. Bottom left is like CO2 breathing, and then bottom right is showing voxel-wise correlation between breath holding and CO2, and they are very well correlated, which is somewhat to be expected because they both are hypercapnic stimulus. And this is showing, the top row is changes in sensory motor cortex during finger tapping. The second row shows in the active voxels from finger tapping, I'm just plotting the amplitude change, the standard deviation from the resting state signal. The third row is a DSST task, which is a cognitive task, and the fourth row is the resting state amplitude for the DSST task. And what can be seen is that typically in the voxels which have large changes during task, those voxels typically, not 100% correspondence, but typically also have large changes, suggesting a good correlation between the two. Again, this is just showing the scatter plot. Again, this is an active sensory motor voxels. Again, the point is, in this case, even if you don't believe in resting state connectivity, you should still collect the data because it could be used as a way to calibrate your signal. So next what we do is, in aging population, there could be difference due to gray matter volume. There could be difference due to cardiac output relating to cerebrovascular reactivity, and then resting state signals. So here what we do is, by using similar method, for any task we can find out how much of the task difference could be attributed to gray matter volume, how much of it can be attributed to breath holding, and how much of it can be attributed to resting state signal. Again, the point here is that in some cases where subjects cannot perform task response, and this is between young and old, in cases where the subject cannot perform breath holding, one can use resting state to calibrate the response. So this can be used as a scaling factor. So the second thing is to look at the spatial map obtained during task activation versus resting state maps related. So Steve Smith had published this paper in PNAS where they had used brain map, and from the brain map coordinate they did ICA, and what they found out was there was a significant overlap between these components, which he called coactivation maps with the resting state map, suggesting that task activation is maybe a subset of resting state signal. However, Martin Menes, then working with Mike Milham's group, showed that the task and rest don't really overlap. So what we did was we used a similar approach using NeuroSynth database instead to look at correlation, both correlation as well as coactivation network. And so on the left is coactivation network. The middle is correlation network, and the last one is just showing correlation versus coactivation. So what we were interested is, okay, fine, we see good overlap between resting state and task activation network, or I should say coactivation network, but what is the difference? So we used graph theory and used global efficiency, mean clustering coefficient, as well as modularity to show that there are differences between coactivation and correlation network. Further, there are specific regions like thalamus, which are more activated in task, while inferior temporal lobe is more activated during resting state. So we have, like, during task, we have higher global efficiency, low mean clustering coefficient, lower modularity. For resting state, we have lower global efficiency, higher mean clustering coefficient, and higher modularity. The next thing we wanted to look at is look at the the dynamic functional connectivity. So I have like 3 minutes. So although there has been number of causes given by what causes functional connectivity, like whether it's physiological noise, whether it's heart rate. So our hypothesis that in addition to these parameters, maybe the dynamic functional connectivity is caused by a third region which modulates the interaction between two regions. So for this, we first wanted to see whether there was indeed an interaction in resting state. Secondly, between different resting state network, whether these was present. And finally, whether these modulator interaction could be modulated by task demands. So this is just showing PPI interaction using REST. We used ICA, and from the different regions that we identify, we can show that for specific regions of the default mode network, different regions are getting modulated. The red means positively modulated, while blue means negatively modulated. So in this case, what it shows is that specific network can influence the connectivity between, for example, salience and default mode, or between default mode and frontoparietal, and so on. And that we can do this we can identify these things both for eyes open, or for very simple tasks like eyes open versus eyes closed. This is using, again, after task to show differences. So then the question was, fine, if during rest there are all these interactions that occur between different regions, could it be that during task also something similar happens? So for this one, we used the human connectome data, and these are the tasks. The last task is the event related, which was from UCLA Open fMRI data set. So this is just doing the voxel-wise analysis for the different tasks. And this is showing by PPI which regions are activated. Again, from this figure, it suggests that even for these kind of tasks, it's not just what we see through GLM analysis. There is many other regions which are activated. Again, this is looking at the whole brain task connectivity matrix for the different tasks, and you can see how different the pattern is, right? If task activation, what we see with GLM was the only effect, then we should not be seeing this. And this is just, again, showing for the different tasks, both positive connectivity and negative connectivity. Again, we wanted to make sure whether this was just a change due to an effect, whether it was method just to PPI, but by using beta series also we see very similar results. So by analyzing whole brain task modulated connectivity, we demonstrate that task modulated connectivity extends far beyond regions that are activated by GLM. And so maybe, with tasks rather than GLM, we have to be more careful how we analyze, because I think it's, so I would like to thank, again, Keith and Ben and for organizing all my collaborators on this. Thank you.